Right now in interstellar space, there are two machines from Earth. Everyone knows the first one. Voyager 1 gets the headlines, the golden record, the title of farthest human object ever built. But there's a second spacecraft out there, moving through a completely different region of the space between the stars, carrying something that Voyager 1 lost decades before it even reached the edge of our solar system. That missing piece turned out to be the single most important instrument for actually understanding what lies at the edge of everything we call home. And because Voyager 2 still had it working when it crossed that boundary, it did something Voyager 1 physically could not do. It measured the plasma directly on both sides of the line at the exact moment of crossing. What that measurement revealed didn't just add to what Voyager 1 found. In several ways, it rewrote it. I'm going to walk you through exactly what happened, why it happened, and why the difference between these two spacecraft matters more than most people who've heard of Voyager realize. Stay with me, because by the end of this, you'll understand why scientists needed 5 separate research papers, published on the same day, just to explain what one spacecraft found in about 24 hours of travel. If you want more stories like this, the real data, sourced and verified, no invented drama, subscribe now, because we're only getting started. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1. If you've ever wondered why the 2 launched before the 1, it isn't a mistake. The numbering reflects the order the two spacecraft were expected to arrive at their targets, not the order they left Earth. Voyager 1 was placed on a faster trajectory, aimed at Jupiter and Saturn before angling out of the solar system entirely. Voyager 2 was given a longer, more demanding route, one that let it do something no spacecraft before or since has done. Voyager 2 is the only spacecraft in human history to visit all 4 outer planets: Jupiter, Saturn, Uranus, Neptune. Every gas and ice giant in our solar system observed up close by a single machine, using instruments built in the early 1970s. The price for that achievement was time. Its path, shaped by a careful sequence of gravitational assists from each planet, meant it reached interstellar space 6 years after Voyager 1 did. Voyager 1 crossed the Heliopause, the true edge of the solar system, in August 2012. Voyager 2 didn't cross it until November 5th, 2018. For those 6 years, Voyager 1's data told scientists that something extraordinary was happening at the edge of the solar system. But the story it could tell was incomplete. And the reason why is one of the most under-discussed facts in the entire Voyager mission. Voyager 1 carried a plasma science instrument, a device built to directly measure the temperature, density, and flow of the plasma around it, both inside the solar system's protective bubble and eventually beyond it. That instrument stopped working in 1980, not at the Heliopause, not in interstellar space. It failed before Voyager 1 had even completed its planetary flybys, decades before the spacecraft reached the boundary that would make it famous. So when Voyager 1 crossed into interstellar space in 2012, it did so blind to the one measurement that mattered most for understanding the boundary itself. Scientists could infer conditions from other instruments, the cosmic ray detector, the magnetometer, the plasma wave subsystem, and they learned a great deal doing it. But inference is not direct measurement. There was a gap in the data, a gap that had existed since before most of the researchers now studying Voyager's findings were born, and there was no way to close it. Voyager 2's plasma instrument never failed. When it reached the Heliopause in November 2018, 41 years after launch, it was still working. For the first time in the history of spaceflight, a spacecraft crossed into interstellar space carrying a functioning instrument capable of directly measuring plasma temperature, density, and speed on both sides of the boundary, in real time, as the crossing happened. That single fact is why Voyager 2's crossing produced a genuinely historic dataset, not because it went somewhere new, Voyager 1 got there first, but because it arrived with the one tool capable of actually reading what was there. Picture the boundary itself for a moment. The sun doesn't just give us light and warmth. It constantly releases a stream of charged particles called the solar wind, blasting outward in every direction at hundreds of kilometers per second. That wind inflates an enormous bubble around our entire solar system, a bubble called the heliosphere. Inside it, everything from Mercury to the icy edges of the Kuiper Belt exists inside a continuous flow of material that originated in our own star. Eventually, the solar wind runs out of energy. It meets the pressure of the interstellar medium, the ancient plasma that fills the space between star systems, pushing back from the other side. Where those two pressures balance is the heliopause. Cross it, and you have left the environment our star controls. You have entered the galaxy itself. For decades, models predicted this transition would be broad and gradual. The solar wind slowly thinning, the interstellar plasma slowly increasing, two environments blending like rivers merging into the sea. Voyager 2's plasma instrument recorded something else entirely. On November 4th, 2018, the spacecraft was still inside the heliosheath, the outer layer of the solar bubble. By November 5th, it was in interstellar space. The transition took less than a day, The 2019 research paper describing the plasma data put the width of the actual boundary layer at under 0.06 astronomical units, a small fraction of the distance between Earth and the Sun. At the scale space physicists normally work in, that's not a gradual blend, that's close to a wall. On November 4th, 2019, exactly 1 year after the crossing, 5 separate research teams published their findings on Voyager 2's Heliopause crossing, simultaneously in the journal Nature Astronomy. That timing wasn't a coincidence. Each instrument team's findings connected to the others, and publishing together let the scientific community see the full combined picture at once, rather than piecing it together over years. Here's what those 5 papers, taken together, actually found. The boundary was sharper than predicted. As already described, the crossing happened in under a day, far faster and more abrupt than the gradual blending models had assumed. The interstellar plasma was hotter than expected. Models had predicted a cold, quiet region just beyond the heliopause. What Voyager 2 measured directly was warmer than that prediction. Not dramatically so in absolute terms, but enough to be a genuine, measurable departure from what decades of theoretical work had calculated. The same data also showed that conditions in the local interstellar medium weren't uniform. They varied. There was a magnetic barrier. Just inside the heliopause, Voyager 2's magnetometer detected a zone where the magnetic field intensity rose sharply above typical levels. A layer of elevated magnetic pressure sitting between the bulk of the heliosphere and the boundary itself. Voyager 1's data had hinted at something similar back in 2012, but Voyager 2 confirmed it with far more detail and showed how it interacts with cosmic rays arriving from interstellar space. This matters because that magnetic barrier is part of the actual physical mechanism that helps shield the inner solar system, including Earth, from high-energy galactic radiation. And the details of how it works didn't match any pre-crossing model. The 2 crossings didn't match each other. Voyager 1 crossed the heliopause in the northern hemisphere of the heliosphere, heading roughly toward the nose, the direction the Sun is moving through the galaxy, where the solar wind pushes hardest against the interstellar medium. Voyager 2 crossed in the south toward the flank, a different part of the boundary entirely. If the heliosphere were a simple, symmetric sphere, both crossings should have looked similar. They didn't. Voyager 2 found a thinner boundary, stronger interstellar magnetic fields, and different plasma conditions than Voyager 1 had recorded 6 years earlier. Both crossings happened at a similar distance from the Sun, roughly 120 astronomical units, despite occurring under very different levels of solar activity, which was itself unexpected. Ralph McNutt and other mission scientists, including Stimatios Kremigis at the Johns Hopkins Applied Physics Laboratory, pointed out directly that this consistency in distance, despite different solar conditions, wasn't something existing models explained well. The interstellar magnetic field pushes back harder than anyone calculated. Both Voyager spacecraft found that the galactic magnetic field just outside the heliosphere was stronger than pre-crossing models predicted, by a factor of 2 to 3. That stronger field exerts significantly more pressure on the heliosphere from the outside. Some estimates, built from the Voyager data, suggest the interstellar medium presses against our solar system's bubble with up to 10 times more force than earlier calculations assumed. Ed Stone, the Voyager project scientist at Caltech, a position he held since before either spacecraft launched, summarized what all of this meant in a single, carefully chosen phrase. He described the 2 Voyagers as showing us not where the Sun ends and interstellar space begins, but how the Sun interacts with the material that fills most of the space between stars and the Milky Way. Not a clean separation, a continuous, dynamic relationship. Here's where this stops being a story about a distant boundary and starts being a story about the planet you're standing on. The heliosphere isn't just a scientific curiosity, it's part of the reason complex life on Earth exists the way it does. Cosmic rays, extremely high-energy particles produced by supernovae and other violent events across the galaxy, stream through interstellar space constantly. Without the heliosphere partially deflecting and slowing them down, the inner solar system, including Earth, would be exposed to significantly more of that radiation than we currently experience. What Voyager 2's data established is that the interstellar medium presses on the heliosphere harder than we thought, which means the heliosphere is somewhat more compressed than models predicted, which means our estimates of how much shielding we actually have, and how that shielding might change as the Sun moves through different regions of the galaxy over millions of years, need to be recalculated using real, measured numbers instead of theoretical ones. This is not a cause for alarm. It's a recalibration. But it's a recalibration that could only happen because one spacecraft, launched in 1977, still had a working plasma sensor 41 years later. There's one more finding from the 2019 papers that deserves its own moment because Ed Stone himself called it the most remarkable result of the crossing, the heliopause leaks. Not metaphorically, literally. Voyager 1, on its approach in 2012, had detected what looked like tendrils of interstellar particles pushing inward through the boundary from outside. Voyager 2, approaching from a completely different direction 6 years later, found something different but related. A trickle of low-energy particles leaking outward from the heliosphere into interstellar space, detected before the spacecraft had even fully crossed the boundary. 2 spacecraft, 2 different entry points, 2 different phases of the solar cycle. Both found evidence that material crosses this boundary in both directions, regularly. Stone's framing was precise. This isn't a wall. It's more like a coastline, with surf running both ways at the interface between 2 oceans. This story isn't finished, and that's the part worth sitting with. As of the summer of 2026, Voyager 2 still has 3 operating science instruments: the plasma science instrument that made the historic crossing measurements possible, the magnetometer, and the plasma wave subsystem. Together, they're providing something no other asset in the history of astronomy has ever provided: a continuous, real-time in situ measurement of conditions in the interstellar medium, taken from a spacecraft physically inside that medium, moving through it at roughly 34,000 miles per hour. But the power is running out, the same way it's running out for Voyager 1. Both spacecraft draw electricity from radioisotope thermoelectric generators, devices that convert the heat from the slow radioactive decay of plutonium-238 into usable power. At launch, each spacecraft's 3 generators produced about 470 watts. That number never goes up. It only goes down by roughly 4 watts every year, as a matter of basic physics. Today, Voyager 2 has slightly more power remaining than Voyager 1, which is part of why it still has 3 working instruments to Voyager 1's 2. To try to slow that decline, NASA's engineering team has been testing an experimental power reconfiguration procedure, internally nicknamed the Big Bang, that restructures how electricity flows through the spacecraft's remaining systems all at once, rather than one change at a time, to avoid triggering the automated fault protection systems built into the 1970s era hardware. Tests of this procedure on Voyager 2 were scheduled for May and June of 2026. If the results hold up, engineers plan to attempt the same procedure on Voyager 1, since a successful outcome could even allow the reactivation of an instrument shut down earlier this year. Voyager 2 goes first specifically because it currently has a slightly larger power margin, making it the safer of the 2 spacecraft to test something this new on. Every command sent to Voyager 2 currently takes more than 16 hours to arrive. Every response takes more than 16 hours to return. A single diagnostic exchange, send a command, receive a result, costs more than a full day before any analysis even begins. That's the environment the small, aging JPL team is working in as they try to keep 2 nearly 50-year-old spacecraft alive. The 5/2019 papers didn't close the book on the Heliopause. They opened new chapters. Why does the boundary sit at roughly the same distance from the sun regardless of solar activity? What actually determines its position, if not the raw strength of the solar wind? What's driving the leakage in both directions, and how does it change over time as the sun moves through different parts of the galaxy? Even the overall shape of the heliosphere is still uncertain. Some models describe it with a long, comet-like tail trailing behind the sun's direction of motion through the galaxy. Others describe something closer to spherical, or even a shape some researchers have compared to a lemon. Voyager 1 and Voyager 2 are sampling only 2 points on that structure, one near the nose, one toward the flank, and their combined, ongoing data remains one of the primary tools scientists have for testing which of these competing models is closer to reality. And underneath all of it sits a harder truth. There's no mission currently funded, designed, or approved to follow either spacecraft into interstellar space. If a new interstellar probe were funded and launched today, using the most aggressive trajectory available, it would still take roughly 25 years just to reach the Heliopause. When Voyager 2's last instrument eventually goes silent, a moment expected sometime in the early 2030s, based on the current rate of power loss, the map it has been building of the interstellar medium stops exactly where it stopped. Whatever lies further out will remain unmeasured in real time for decades. Step back for a second and look at the full list of what this one spacecraft launched August 20th, 1977 has actually accomplished. It's the only spacecraft ever to visit Uranus, discovering new moons and rings during its January 1986 flyby, and measuring the planet's extreme axial tilt along with a magnetic field so oddly offset from its rotation axis that it still challenges models of how planetary magnetic fields form. It's the only spacecraft ever to visit Neptune, discovering new moons during its August 1989 flyby, the last planetary encounter of the entire Voyager program, measuring supersonic winds and capturing detailed images of Neptune's moon Triton, including active geysers erupting material into its thin atmosphere. It confirmed the active volcanism on Jupiter's moon, Io, that Voyager 1 had first detected. It returned images of Europa's fractured icy surface that helped seed decades of scientific interest in that moon as a potential habitat for life, interest that eventually led to NASA's Europa Clipper mission. All of that from hardware designed in an era before the internet, before personal computers, before GPS, using engineering philosophies nearly 50 years old. A spacecraft that was only ever expected to operate for 4 years. None of this data would exist without a very small, very specific group of people at JPL who understand how to talk to hardware that predates almost every modern engineering standard. The original Voyager engineers have largely retired. The people who replaced them had to learn programming languages and spacecraft design philosophies from the 1970s just to issue commands the spacecraft can actually understand. This isn't the kind of knowledge you can look up in a textbook or pull from a modern aerospace curriculum. It's institutional knowledge, carried by a small number of specific people, refined command by command over decades of keeping 2 aging machines alive across a communication gap measured in hours. That team has already been tested by real crises, not hypothetical ones. In 2023, Voyager 1 began transmitting corrupted, unreadable data for months. Engineers eventually traced the problem to a single memory chip that had physically degraded after nearly 5 decades of exposure to cosmic radiation. The fix required splitting the affected software into smaller sections, relocating them to different areas of the spacecraft's limited remaining memory, and carefully reconnecting everything to function as a whole, all through a communication loop where a single round-trip exchange took roughly 44 hours. It worked, and by mid-2024, the spacecraft was transmitting clean data again. Voyager 2 has had its own close call. In 2023, a routine command accidentally caused the spacecraft's antenna to tilt slightly off target, cutting off communication entirely for about 2 weeks until the Deep Space Network's Canberra facility in Australia was able to send a signal strong enough to reset the antenna's orientation and restore contact. 2 weeks of data from that specific stretch of interstellar space is simply gone. Not corrupted, not delayed, permanently unrecorded, because a spacecraft moving through space only passes through each point once. These recoveries matter for understanding what a project like the Big Bang power procedure actually represents. It isn't a routine software update. It's an attempt, using institutional knowledge that exists almost nowhere else on Earth, to physically restructure how electricity moves through a spacecraft that has already survived multiple near failures, using nothing but radio commands sent across a gap the speed of light itself takes more than half a day to cross. It's worth being precise about how different the 2 Voyager Heliopause crossings actually were, because the contrast is what makes Voyager 2's data so valuable to researchers even now. Voyager 1 crossed in August 2012, heading roughly toward what scientists call the nose of the heliosphere, the direction the sun is moving through the galaxy, where the solar wind pushes hardest against the surrounding interstellar medium. It crossed without a working plasma instrument, so researchers had to reconstruct what happened using cosmic ray data, magnetic field readings, and plasma wave measurements, all useful, but all indirect. Voyager 2 crossed in November 2018, more than 6 years later, heading toward the flank of the heliosphere rather than the nose, at a different point in the 11-year solar activity cycle with a fully functioning plasma instrument. That combination, a different location, a different point in solar activity, and direct plasma measurements, is exactly why the 2 crossings didn't produce matching pictures of the boundary. A single data point can only tell you about a single point in space and time. 2 data points from different angles start to reveal actual structure. That structure is what the 5 2019 papers were built on, and it's the foundation researchers are still using today to model the heliosphere's true asymmetric shape, rather than the simple sphere most people picture when they think about the edge of the solar system. It's worth being honest about where this is heading, because the ending isn't in question. Only the timing is. Both Voyager spacecraft lose roughly 4 watts of usable power every year, a direct consequence of the fixed decay rate of the plutonium-238 inside their generators. That decay doesn't slow down, speed up, or pause. It's one of the most predictable processes in physics. At some point in the early 2030s, by current mission estimates, the power output of each spacecraft will drop below the minimum threshold needed to operate any remaining instrument, and each will go silent. Not because something breaks, but simply because there won't be enough electricity left to keep listening equipment or transmitters powered on. When that happens to Voyager 2, the only real-time, direct measurement of interstellar plasma from the southern side of the heliosphere will stop. There is, as of today, no mission funded or built to replace it. The interstellar probe concepts that have been proposed within NASA remain exactly that. Proposals, with strong scientific justification, but no launch date and no budget. Even under the most optimistic mission design, a new spacecraft launched today would need roughly a quarter century just to reach the boundary Voyager 2 already crossed in 2018. That's the real weight behind every additional month of data Voyager 2 manages to send back. It isn't just extending a nostalgic old mission. It's extending the only live window our species currently has into a region of the universe that, once the spacecraft goes quiet, we may not be able to directly observe again for a generation. It's easy to focus entirely on the Heliopause crossing and forget that Voyager 2 spent its first 12 years doing something almost as remarkable, actually visiting the outer planets one after another using a single set of instruments across distances and timescales no mission has attempted since. At Jupiter in 1979, it confirmed the active volcanism that Voyager 1 had first spotted on the moon Io, capturing images of a 200-kilometer-high plume erupting from the volcano Prometheus. At Saturn in 1981, it returned detailed images of the ring system's structure, revealing complexity that ground-based telescopes had never been able to resolve. Neither of those flybys was small in scientific terms, but they were really a warm-up for what came next. The Uranus flyby in January 1986 remains, to this day, the only close-up data humanity has ever collected from that planet. Voyager 2 discovered 10 previously unknown moons and 2 new rings, measured the planet's extreme 97, 77-degree axial tilt, and found a magnetic field so strangely offset from the planet's rotation axis that it still challenges current models of how planetary magnetic fields form in the first place. No other spacecraft has been back since, and none is currently funded to go. The Neptune flyby in August 1989 was the final planetary encounter of the entire Voyager program, and arguably its most dramatic. Voyager 2 discovered 6 new moons, including Proteus, a moon large enough that it probably should have been detectable from Earth long before Voyager arrived, had anyone known exactly where to look. It measured wind speeds on Neptune reaching roughly 2,400 kilometers per hour, the fastest ever recorded in the solar system at the time, and it turned its cameras toward Neptune's largest moon, Triton, where it found active geysers shooting nitrogen gas and dark material several kilometers into the moon's thin atmosphere. Evidence that helped convince scientists Triton wasn't a moon that formed alongside Neptune at all, but a captured Kuiper Belt object, its surface reshaped over billions of years by tidal heating from a slowly circularizing orbit. None of that data has been superseded. Nearly 40 years later, Voyager 2's flyby measurements remain the primary source of direct, close-up scientific knowledge about both ice giants. Every textbook diagram of Uranus and Neptune, every model of their atmospheres and magnetic fields, traces back to roughly 48 combined hours of close observation from a single spacecraft in the late 1980s. That's the machine that, decades later, carried a still-functioning plasma instrument through the edge of the solar system and gave researchers their first direct read of what lies beyond it. The same spacecraft, the same hardware, the same 49-year uninterrupted engineering effort. First mapping 4 planets in detail no mission has matched since, then mapping the boundary of the solar system itself. Voyager 1 will always be remembered as first. First to leave the solar system, first to cross into interstellar space, first to carry the golden record into the dark. That's a real and permanent achievement, and nothing about Voyager 2's story diminishes it. But being first isn't the same as seeing clearly. Voyager 1 crossed the most significant boundary in our cosmic neighborhood without the one instrument built specifically to read it. Voyager 2 crossed that same kind of boundary 6 years later from a completely different direction with that instrument still alive. And what it measured didn't just confirm what Voyager 1 had found. In places, it contradicted it. It complicated it. It filled in a gap in human knowledge that had existed since 1980. That's the story headlines rarely tell, because second spacecraft to do something doesn't sound as dramatic as first spacecraft to do something. But in this case, second is where the real data actually came from. Right now, tonight, both spacecraft are still out there. Voyager 1, roughly 16 billion miles from Earth. Voyager 2, roughly 13 billion. Still transmitting, still measuring, still sending back a signal built from technology older than most of the scientists currently analyzing it. Voyager 2's plasma instrument is still turned on. It's still reading the density, temperature, and motion of the plasma between the stars, one measurement at a time, building a map that no other instrument in human history has ever built, from a place no other instrument has ever been able to reach. When it finally goes quiet, and it will sometime in the years ahead as the power keeps declining by 4 watts a year with no way to reverse it, that map will stop exactly where it stopped. And it will stay that way for decades, until some future mission, not yet funded, not yet designed, not yet launched, makes the same journey and picks up where it left off. Until then, the signal is still coming. Faint, delayed by more than 16 hours each way, but still coming, still carrying real measurements from a real place that our species has only ever managed to reach twice. If you want to know what happens when the Big Bang power test results come in, whether Voyager 2 gets more time, and what that means for Voyager 1's own attempt later this year, subscribe and turn on notifications. This channel covers the actual data, the actual published research, and the actual mission updates as they happen, without inventing anything the instruments themselves didn't measure. What Voyager 2 found at the Heliopause in 2018 is one of the most significant scientific datasets of the last decade, and most of the world still doesn't know what happened. We're going to keep telling this story properly, one confirmed update at a time. Thanks for watching.